Welcome back to AI Paper Podcasts. Today, we are diving into a really common challenge, something that probably plagues every ML engineer trying to optimize a production RA system, domain specificity. You've tuned your retrieval stack, maybe you've picked a really powerful embedding model, often one of those proprietary black box APIs like, say, OpenAI's.
Right, the big guns.
Exactly. But then you find that, well, without that specific domain knowledge, whether it's medical terms or tricky financial jargon, your accuracy just kind of hits a ceiling.
And that's precisely the problem this paper tackles. It's called MAFIN, Enhancing Black Box Embeddings with Model Augmented Fine-Tuning.
MAFIN, okay.
Yeah, MAFIN. So it acknowledges you can't tweak the parameters inside that proprietary model. So instead, the idea is to augment or add to the fixed output from the black box model with a small trainable model, what they call a white box model.
Okay, so you keep the powerful black box one as is, but you add a little custom model alongside it.
Exactly. And this isn't just some, theoretical exercise. It's actually a huge efficiency play. You get to use the really high quality general representations from the expensive black box, but you only pay the compute cost for fine-tuning a tiny task-specific model.
Which sounds much cheaper.
Way cheaper for the result. MAFIN delivers a pretty stable and significant performance boosts for these custom RX tasks.
Oh.
We're seeing gains over 5% on supervised retrieval benchmarks in specialized areas like finance.
Wow, 5% is quite a jump.
It is, especially compared to just trying to fine-tune an open-source model by itself. MAFIN basically gives you this cost-effective, personalized domain adaptation for models you can't actually peek inside. It's pretty neat.
Okay, Kate, let's really unpack this then. Let's set the stage a bit more. For anyone building AI systems these days, RRA retrieval, augmented generation, it's pretty much the standard way to go, right?
Oh, yeah, absolutely. It's become dominant.
And largely because it helps with two kind of fundamental weaknesses of LLMs.
Right on. First, you've got the knowledge cutoff problem. LLMs don't know recent events or your private data.
And second,
there's the big one, hallucination.
Yeah.
The model making stuff up. RRAG tackles both by hooking the LLM up to an information retrieval system.
So it can pull in external, hopefully verifiable facts from your own databases or the live web.
Exactly. It grounds the generation in real information.
And the success of the whole RRAG pipeline, well, it really hinges on how good that retrieval step is, doesn't it?
Absolutely critical. We mostly rely on dense retrieval methods now. So you map queries and documents into this shared vector space.
Right, using embeddings.
Using embeddings, yeah. And relevance is basically determined by how close those vectors are, usually measured by cosine similarity.
And for those really high-stakes areas, you mentioned finance, maybe legal, medical, you absolutely need that retrieval to be spot on. You need domain-specific tuning.
You really do. You need to maximize the chance that you pull back the exact piece of information needed.
But here's the catch. The best-performing embedding models out there, a lot of them are those black boxes we talked about. You get an API endpoint, you get a vector back. But you can't actually fine-tune the model weights on your specific data.
And that's the gap. That's the engineering hurdle MAFIN is designed to jump over.
Okay, so let's get into the MAFIN architecture itself. How does it work?
The core idea is, like we said, brilliantly simple. If you can't fix the black box embedding, let's call it EBA, then just augment it. Add a trainable one, EBFA, alongside it.
And how do they combine them?
They just concatenate the two vectors, stick them end to end to create this new enhanced embedding, which they call EBFA.
Okay, wait a second. Let's think about the practical side here. If my black box embedding is, say, N124 dimensions.
Pretty standard, yeah, like ETA 002.
And my trainable one, even if it's small, might be, 768 dimensions.
Could be like a BGE base or something.
So now my final MAFIN embedding is 1,792 dimensions. That's significantly bigger. Doesn't that blow up my vector index size? And what about retrieval speed? Does the latency double?
That is absolutely the key trade-off you're making. You're increasing the dimensionality.
Right.
And yes, that means a larger memory footprint for your index and potentially slower retrieval, though maybe not double, depending on the indexing strategy. The paper implicitly argues that the gain in relevance, the accuracy improvement, is worth that extra cost.
Okay.
Especially because retrieval is usually much faster than the final LLM generation step anyway. But, and this is important, they're very strategic about that trainable model, LLM. They specifically use small white box models like BGE small or BGE base.
To keep that extra dimension count and the training cost down.
Exactly. Minimize the explosion, keep the fine-tuning cheap and fast. That's central to the whole value proposition.
Okay, that makes sense. So back to the math they concatenate, and then there's this normalization step you mentioned.
Yeah, that's right. So the formula is basically AFIN, Finden, SOHCAHTOA the whole, divided by the square root of 2. Why that specifically?
Okay, so if you assume both the original black box embedding AFIN and your trainable embedding AFIN are already normalized, meaning they have a length, or L2 norm of 1.
Which is common practice for models used with cosine similarity.
Right. Then dividing the concatenated vector by the square root of 2 ensures that the final AFIN vector also has a norm of 1.
Ah, okay. And why is keeping that unit norm so important here?
It preserves the nice mathematical property of cosine similarity. When your vectors are unit length, cosine similarity is just the dot product.
Simpler calculation?
Simpler, yeah. And by keeping AFIN normalized, the final relevance score calculation actually becomes equivalent to just summing up two separate dot products, one using the black box part and one using the trainable part.
Interesting. So you're effectively adding the relevant signals from both models. Precisely. You're explicitly combining their opinions on relevance, which is how you potentially increase the overall representational power. Though they do note that the score factor doesn't actually change the ranking of items, so you could potentially ignore it in practice to save a tiny bit of computation, but mathematically, it keeps things clean.
Got it. They also mentioned another variation, Lambda-MAFIN. Did that turn out to be better?
Yeah, they explored that. The idea with Lambda-MAFIN was to use an unnormalized trainable embedding, let's call it the theta, so don't force it to have a length of 1.
Right. The thinking was that the magnitude or norm of this trainable vector could then act as a kind of learned weight. If the model learned a large norm for theta, it would implicitly give more weight to the trainable part in the final combined score, and vice versa.
Ah, so the model could learn, say, trust the black box 70% and the trainable part 30% based on the data.
More flexible.
Exactly, more flexible weighting. But interestingly, in their experiments, the standard MAFIN approach, just concatenating and normalizing, performed pretty much just as well.
Huh.
It seems like just optimizing that small white box model about theta during the fine-tuning was enough to get the domain adaptation they needed without the extra complexity of learned weighting. So they kind of noted Lambda-MAFIN was interesting, but deferred really digging into its potential advantages for future work.
Okay, so the standard MAFIN architecture is the main focus. The real magic then seems to be in how you train that small white box model, AF theta. How did they set up the fine-tuning?
Right, that's crucial. They frame it as a learning to rank problem, which makes sense for information retrieval.
You want the model to learn how to rank the passages correctly for a given query.
Exactly. They used a probabilistic approach based on something called the Placket loose model. This model is pretty sophisticated. It uses graded relevance labels, if you have them, to figure out the probability distribution over all possible rankings of candidate passages.
So if you have labels saying passage A is highly relevant, score 2, B is somewhat relevant, 1, and C is irrelevant, row.
Yeah.
The model tries to learn to rank them A, then B, then C.
That's the idea. But there's a problem. If your corpus is huge, the number of candidate passages, let's call it dollars, can be massive, thousands or millions.
Right. Calculating probabilities over all possible permutations of millions of items sounds expensive.
Intractable, basically, yeah. So this is where they introduced a really clever efficiency trick.
The approximation using the temperature parameter.
Exactly. They looked at what happens when you take the temperature parameter, tack on the Placket loose loss function, and let it approach 0.
Okay, what does that do mathematically?
It drastically simplifies the objective. Instead of trying to model the probability of the entire correct ranking, the loss function essentially collapses to focus on just one thing, maximizing the probability that the single most relevant item is ranked higher than all the other candidates.
Ah, so you stop worrying about the exact order of less relevant items and just focus on getting the best one to the top. Much simpler.
Much simpler and much more computationally feasible for large K.
And this simplification led to that surprising connection they found.
It did. This is pretty cool, actually. When they worked through the math of that approximation, the resulting training objective turned out to be mathematically equivalent to the InfoNC loss.
InfoNCE. That's the loss function everyone uses in contrastive learning, right? Like in some CLR or CLIP.
Exactly. Information noise contrastive estimation. It's all about pulling positive examples, like the query in the most relevant passage, closer together in the embedding space, while pushing negative examples further away.
Wow. So they started with a formal probabilistic learning to rank framework and ended up with the standard contrastive learning objective.
Yeah. It provides this really neat, novel, probabilistic justification for why InfoNC works so well for retrieval tasks. connects these two big ideas, learning to rank and contrastive learning. That's a significant theoretical insight on its own, beyond just making MAFIN work.
That's really interesting. Okay, so that covers the supervised case, where you actually have query passage pairs with relevance labels. But what if you don't? What if you're, say, a company with just a huge pile of internal documents, but no one has labeled which passages answer which potential questions?
Right, the unsupervised scenario. This is super common. You have the passages, but not the query passage pairs.
So how does MAFIN handle that? You can't use the learning to rank approach without labels.
This is where they cleverly bring in another powerful tool, a pre-trained large language model, like ChatGPT.
Ah, okay. How do they use it?
They basically use the LLM as a synthetic query generator. For each passage in your unlabeled corpus, they feed it to the LLM with a simple prompt. Something like, generate a likely query that this passage would be a good answer for.
So you automatically create your own training data, generating a plausible query for every single passage you have.
Exactly. You end up with a whole set of synthetic query passage pairs. It's not perfect. Obviously, the generated queries might not cover every possibility, but it gives you a starting point.
Okay, so now you have pairs. How do you train with those? You don't have graded relevance scores.
Right. So they make a simplifying assumption. For a given generated query and its source passage, they treat that pair as the single positive example in the batch. Binary relevance, score 1.
And everything else in the batch?
All other passages in that training batch are treated as negative examples, relevance score 0.
Okay, so you've basically turned the problem from a complex ranking task into a much simpler classification task almost. For each query, identify the one correct passage out of the batch.
Precisely. It becomes a single label classification setup, which you can train using standard maximum likelihood estimation, MLE. You're maximizing the probability of picking the correct passage for the synthetic query.
Making the whole unsupervised fine-tuning process really quite scalable and practical, even without any human labeling effort.
Yep. It leverages the LLM's ability to understand context to bootstrap the training data for the embedding model. Pretty smart.
It sounds elegant, both the supervised and unsupervised training. So the big question, did it actually work? How did MAFIN perform when they tested it on real, specialized data?
They picked two pretty distinct domain-specific datasets for validation.
Right. What were they?
First was FAQAD 2018. This is financial question answering data pulled from Stack Exchange. So lots of specific financial terms, concepts. Getting the right answer really matters there. It used binary relevance labels, 0 or 1.
Okay, finance. And the second?
The second was NF Corpus. This one's focused on medical information retrieval based on content from nutritionfacts.org.
Medical info. Definitely high stakes.
For sure. And NF Corpus is interesting because it uses graded relevance, score 0 for irrelevant, 1 for somewhat relevant, and 2 for highly relevant.
Which really tests the ranking capability, not just finding a relevant document, but putting the most relevant ones first.
Exactly. And that's why they leaned heavily on metrics like NDCG at K-normalized discounted cumulative gain.
Right. NDCG is crucial for graded relevance because it heavily penalizes models that rank a highly relevant item below a less relevant one. Recall that K is important too, but NDCG really captures that ranking quality.
Precisely. So for the implementation details, the black box model was OpenAI's text embedding at a 002, a very strong baseline.
Makes sense. And the trainable white box models.
They used BAAI's BGE models, specifically BGE base for the VKA dataset and the even smaller BGE, small for NF Corpus.
Again, highlighting that strategy of using small, efficient models for the augmentation part. They picked models that were good, but known to have a performance gap compared to ADA 002 on their own.
Right, so there was clear room for improvement via fine-tuning.
Okay, so how did MAFIN actually do against the other approaches? They compared it to several baselines, right? Like just fine-tuning the BGE model alone.
Yep. They compared against 1, just fine-tuning the BGE model, only fine-tuning. 2, simply concatenating the ADA 002 and BGE embeddings without any fine-tuning, simple concatenation. 3, fine-tuning BGE first, then concatenating, fine-tuning, and concatenate. 4, and trying to learn a linear transformation matrix to adapt the black box embedding.
Okay, a solid set of comparisons. What were the results?
The results were pretty clear-cut. The supervised MAFIN, which they called MAFIN Sup, consistently gave the best and most stable improvements across both datasets.
Better than the original black box model.
Yes. Crucially, it surpassed the performance of text embedding ADA 0002 on its own, which is exactly what you want, enhancing the state-of-the-art black box for your specific domain.
Can you give us a feel for the numbers, that 5% gain you mentioned earlier?
Absolutely. So on that FQP 2018 financial data, MAFIN Sup improved recall at 3 by up to 6.86% compared to just fine-tuning the BGE model alone.
That's a really substantial gain in retrieval accuracy. Imagine finding the right financial answer almost 7% more often in your top 3 results.
Exactly. And it achieved this just by training that relatively small BGE-based model alongside the fixed data 002 output.
What about the cost? You emphasized how cheap the training is. Was it fast enough that you could imagine, say, rerunning this fine-tuning daily or weekly if new domain data comes in?
Oh, absolutely. That's the core engineering advantage. Because you're only training the small augmenting model, the vast majority of the parameters in the black box model are frozen. The actual fine-tuning process is incredibly fast and requires minimal resources.
So it opens the door to continuous, customized fine-tuning loops.
Precisely. Something that would be prohibitively expensive if you were trying to fine-tune the entire massive black box model itself, even if you could. MAFIN makes frequent domain adaptation totally feasible.
And even the unsupervised version, MAFIN Sup, using those LLM-generated queries.
Even that performed well. It still showed noticeable gains over the original black box model. It wasn't quite as good as the supervised version, which makes sense, but it clearly validated the strategy of using synthetic data when you don't have labels. It still works.
That's really useful for organizations that just have lots of raw text.
Definitely.
They also had that interesting finding about simple concatenation, just sticking the embeddings together without training. Sometimes even that beat the black box model alone.
Yeah, that was a fascinating side note. It suggests there's a kind of inherent bagging or ensemble effect.
Like combining 2 different perspectives.
Kind of. You've got the general knowledge from the powerful black box, add a 002, and maybe slightly different knowledge captured by the pre-trained open source model, BGE. Just putting them together gives you a bit more robustness, covers more bases.
But MAFIN, with the actual fine-tuning, was still better.
Oh yeah, MAFIN was superior because it specifically optimized that added white box component for the target domain. It makes the combination truly synergistic, not just additive.
And what about that linear transformation idea, just trying to tweak the black box embedding with a learned matrix?
They confirmed that was pretty ineffective. The results were inconsistent, and often it actually hurt performance compared to the original black box model.
So it seems like you really need the representational power of a dedicated, albeit small, neural network component to handle the complex, nonlinear patterns in specialized domains. A simple linear fix isn't enough.
That seems to be the conclusion, yeah.
Yeah.
True domain adaptation needs that extra flexibility.
Okay, so let's synthesize this.
Okay.
What's the big takeaway for, the ML engineer listening right now who's building or tuning a RRA system?
I think the main message is that MAFIN provides a really practical, effective solution to that core RRA dilemma. How to get domain specificity when using powerful but inaccessible black box embedding models.
It bridges the gap.
It really does. By smartly augmenting the black box output with a small, efficiently trainable white box model, MAFIN delivers significant performance gains without the huge cost or complexity of training massive models from scratch or needing full access to proprietary ones.
So you get the best of both worlds, in a way. The scale and quality of the big model, plus the customization of a small one you control.
Exactly. You leverage the state-of-the-art representations, but add your own targeted improvements cheaply and quickly. It supports supervised tuning if you have labels, and unsupervised tuning with synthetic data if you don't. It seems very flexible.
The paper focused on text retrieval for RRA, obviously, but did the authors suggest this approach could be used elsewhere?
They did. They suggested the general framework, augmenting a fixed, powerful embedding with a small trainable one, could likely be beneficial for other downstream tasks that rely on embeddings. Things like text classification, clustering, semantic search beyond just RRA.
So the core model augmentation idea might have broader applications.
Potentially, yeah. It's a neat architectural pattern.
All right, this has been super insightful. It really feels like MAFIN offers a tangible path forward for improving RRA in specialized areas. So maybe a final thought to leave our listeners with. If a method like MAFIN allows, say, a smaller company or even a startup to get, let's imagine, 95% of the performance they might get from having full access to fine-tune a giant proprietary model, but they can do it at maybe 1% of the training cost.
A huge cost differential.
Does that start to change the game? Does the inherent value or the moat around those massive closed proprietary models start to shrink? If clever adaptation methods like MAFIN become widespread, does it shift the competitive advantage away from just having the biggest model towards being the smartest at adapting existing models?
That's a really interesting question. It definitely lowers the barrier to achieving high performance in specialized domains.
Something to think about as you design your next RAG pipeline, or maybe even your next business model around AI. Thanks for breaking down MAFIN for us today.
My pleasure. It's a really practical and clever piece of work.